Morning. Again, my name is Nasir Manin. I'm principal engineer here at Connecticut Center for Advanced Technology. Welcome if you haven't been to the Advanced Technology Center here before. Um, Today we've got a exciting lineup. We've got a number of technology partners that are very eager to show you some of the most recent advancements in their particular solutions. But before we begin, a couple of housekeeping. We are an ITAR facility. If you can refrain yourself from taking photos or videos, that would be much appreciated. Restrooms are located just behind this wall here. If you go around to the other side, there's two of them. Either of them are can be used. Fire exits and assembly location, you would just head straight back out the door that you came in from through the reception area. And at the end of this presentation, you may receive a link via email. We like to know how we do in these presentations and just like to get that feedback to understand if what we're presenting is relevant to you, or if there's other suggestions, other technologies you'd like to see and for us to present, we'd like to hear about that. So CCAT, we are a private nonprofit organization. Our goal is to get as much state funding allocated for advancing manufacturing and pulling in federal money to help along the same cause. Our vision is a transformative solutions for a connected world, and our mission is to lead the advancement of applied technologies, power the workforce of the future, and inspire change. So as I said, CCAT is an applied technology demonstration and training center that validates, demonstrates, and assists with the adoption of leading edge technologies to enable a resilient supply chain and industrial base while providing vital training and upskilling. You're sitting at the Advanced Technology Center where we have a lot of technology. Some of it's purchased by us, some of it is consigned. The purpose of this lab is for you to test out what these technologies can do. So if you've ever wished to have a sandbox to play in, this is the sandbox. If you have a process that you want to test out, you want to try additives, you want to try non-contact inspection to see if that will work on your parts. If you wanted to explore automated welding, bring us your problems. We'll test it here. We'll develop the processes so you don't have to take the time at your shop floors. That's what we're here for. Please do consider us your R&D arm. So some of the ways in which you can take benefit from us, we hold a number of introductory workshops throughout the year. We do them in person as well as virtual or hybrid. The introductory workshops are really set up so that we can introduce you to technologies that you may not know exist, technologies that are up and coming. And then we follow that up with technology demonstration projects. So the demonstration projects are more in depth. We actually either have the technology here or present them virtually via a technology partner and run a particular process on a part. So that can be a demonstration part that we have, or if you're interested in seeing how that process or how that technology can be beneficial to you, we can take your parts and run it through the technologies to show you how it can impact you directly. To help support onboarding that technology, we have a number of grant programs available. We'll talk more in depth about the different pots of money that are available to you. But we also provide engineering support to help onboard the technology. And then we follow that up with technology training. So we are standing up our digital thread lab at our other building on Pickens Street. Courses will be available come January. And these are no-cost courses for you to understand and learn how to leverage model-based workflows. So the Advanced Technology Center, you're on the side of the Advanced Design Automation and Metrology Lab, so it's the digital side. On the other side, we have the Additive Technologies Optimization and Machining Lab. And then at another facility with Goodwin, we have our Advanced Composites Lab. So before we get into the agenda, and handing it over to the technology partners, I just wanted to briefly um, explain what is Industry 4.0, kind of set the premise as to why we're going to be discussing some of the technologies we're going to be going through today. So in order to understand Industry 4.0, let's take a quick look at Industry 3.0. Really, the advancement from 2.0 to 3.0 was the inclusion of computerized systems, right? CNC controlled systems, automation, robotics. When we talk about Industry 4.0, it is providing those computerized systems the ability to sense, feel, think, and adjust on their own. So in a simple sentence, that's about as best as I can do to explain the difference between Industry 3.0, which is automation, and Industry 4.0, which is autonomy. So what are the benefits of autonomy? Well, if you have systems that can adjust on their own, that can account for manufacturing variability, that can program production processes automatically, you obviously have improved productivity, improved efficiency, better flexibility and agility. That's the biggest one. The flexibility and agility. If you're a high mix, low volume type of manufacturing facility, this is key. This is key to be efficient at being able to produce the programs that make those parts and then to actually execute running those programs, but guaranteeing that the parts always come out good. And then increase profitability. All the 3 points above affect your profitability. So the image on the left there, that encompasses pretty much all the technologies that fall within the Industry 4.0 umbrella. Today, we're going to be talking about big data and analytics. We're going to be talking about robotics, and we're going to be talking about a little bit of IoT. So let's talk about model-based definition. This is really in all the technologies you're going to see today, each one of these software packages leverages model-based definition. And so traditionally, you as a manufacturer may receive from your customer a 2D drawing to produce a part. You may receive a CAD model along with that 2D drawing, but the drawing itself is contains the design, it contains the requirements, it contains the tolerances that each feature has to be produced to. And so that's the document that you have to go back to. It's never the CAD, it's always the drawing. The issue with that format is that it's a human consumable form. I can read it, I can make conscious decisions as to how I'm going to produce the parts based on the information that's contained in that 2D drawing. For example, if I have a hole with a tight tolerance, I'm going to choose to run a certain process on it, choose a certain kind of tool, put it on a specific kind of machine. These are decisions that a person is making by seeing that information. Model-based definition takes that human consumable data and converts it to a digital form. The benefit of having it in a digital form is now software can see that information and then make their decisions on how to produce the programs to produce those features on the part. But in order to leverage this information, you have to set up your manufacturing software in order to consume that data properly. In other words, you set up the strategies, the logical decision making that you take when you see information on the drawing. You want to set that up in the software such that if it sees the CAD model, it knows the geometry that needs to be produced from the CAD geometry itself, and then attached to that geometry, you have additional information. So, for example, a tolerance band. And if the software sees that it's a tight tolerance versus a loose tolerance, it sees the material that that part has to be made from and other specifications that might be in that MBD file. Now it has the logic tree in order to make the same decisions that you typically would make, but now automatically. So there's a huge benefit. And what you're looking at here is an example of what might be contained in an MBD package. So you have your requirements, your product design, your PMI. Typically, you'll see this as a technical data package from OEMs. And you can use this technical data package across all your different manufacturing disciplines. So for analysis, costing, manufacturing, part production, quality control, as long as you have a data management system such as like a PLM system or a PDM system, that will be the repository and the system that actually manages that MBD file and all the information that you attach to it. So for example, if from your customer you receive a technical data package, you put it into your PLM system, now your manufacturing engineers can pull that down, add information to it in terms of a production program, put it back into PLM, your inspection folks can take that down, add inspection data to it or inspection program information to it, and now your costing folks can take that down and be able to cost that part out. So it acts as a central repository. It does file revision changes, revision control, but it's key. It's key to managing that technical data package. So for today, having kind of laid now, the groundwork as to what model-based definition is, let's take a look at how we actually consume that data. We're going to look at technology from Capvidia, easy and powerful MBD workflows, CAD translations, and validation software. So it's very important to understand that in native CAD, you can have geometry, you can have PMI, but how do you use this in other software? So if, for example, your customer is using Siemens or they're using SolidWorks or Creo or CATIA, you want to be able to use the data that they're putting into this model, the intelligence that's being put into this model across different software. And so there are standards that allow neutral formats, so step 242, QIF. But in terms of translating from native CAD to the neutral formats, you could run into some problems, and Capvidia has solutions to overcome those issues. So you're going to see some of that today. Visual components, we have Brian Knudsen and his team there to present automated welding processes by importing QIF, which is one of the neutral formats for MBD, and automatically generating welding paths using the callouts that's embedded within the QIF format. And then we're going to look at automated visual inspection by Corey Merchant, and this is all based on model-based definition. And then we'll take a look at automated dimensional inspection using structural light scanning, and then running that data through PolyWorks to populate an inspection report. And then we'll give some time for question and answers at the end. So if you do have questions throughout the presentations, please do write them down. We'll give you a chance at the end to ask all the questions. Lyle, over to you.
Yeah, thanks, Nasser. All right. Hope everybody can see my screen. Good. My name is Lyle Fisher. I'm the Senior Technical Manager for Capvidia. And today I'm going to share with you some MBD workflows that we're doing with a lot of our customers. The customers we work with cover a large range of industries. So you have automotive, aerospace, defense, medical, agriculture, and consumer products. So a lot of these companies, they're already taking advantage of model-based definition, and so I'll share with you some of the things they're doing. But let's talk a little bit about QIF. I know Nasir mentioned it. What is QIF? Well, it's an ISO standard. It stands for the Quality Information Framework, and it's really a CAD format with really a lot of powerful things for MBD. So really the MBD, you can create some quality plans, and you can actually start to look at quality results. So as you can see, there's a wide support already for the ISO QIF format. The DMSC is in charge of that. But today we're going to be we interface with all these companies And PolyWorks, Kitov, and visual components. We're going to cover those bases today. I'm going to show you a MBD workflow for first article inspection first. So what this is about is, as Nasir said, it starts with the CAD system. You author the MBD in a CAD system, and NX, Creo, SolidWorks, CATIA, whatever. And then you publish that. And we publish it to QIF. And as yet, QIF is this CAD format that we can pull in our software, and we create what's called the bill of characteristics. Basically, what it is do you want to inspect, and how do you want to inspect it? So you can basically generate an inspection plan. This does the ballooning. I mean, this is the critical part of the MBD workflow, where you gather this information from MBD and you determine what it is you want to inspect, and then you pass that downstream. So we can pass that to Excel, to our partner NetInspect. We can work with welds. We publish to 3D HTML, which I'll also show you. And from there, it goes off to inspection. I'm not going to show I'll let the PolyWorks folks do that today, but I'm just going to show you a simple workflow using Excel. And finally, what we want to do, and this is the exciting part about an MBD workflow, is that these arrows are all going downstream. But as we get measurement results out of the inspection software, or Kitov, or visual components, we can actually harvest that data and complete the loop. So I'll show you that. So let's start with a simple workflow here for first article inspection. So this is NX. So again, the starting point is any CAD system. And so you'll see the different model views in this NX file. So again, there's no 2D drawing, of course. We're working in MBD. You can have visual inspection information into this file. So inside, now we publish to QIF, okay? So this takes this data out of NX, and now it puts in a neutral ISO standard format. And on the left, you see our product MBD And first thing we're showing you is that, the structure is maintained. We have not only all the model views, but we maintain the balloons, in this case from NX. So we already have some traceability built into the QIF framework to take this data downstream. And now we're just going through and showing you different model views and different annotations that we're going to be inspecting. And here's some visual surface information for Kitov. We've got each particular model view has its own characteristics that they're interested in. From here, we do our bill of characteristics. Now, this does the ballooning in one click. We're able to export this out to an Excel form, whether it be AS9102 or a customized form, what we do for a lot of our customers. So this is called the initial sample inspection report. You can see all the balloons are in column 1, and you can click on a balloon. You can go to a 2D view of that balloon so you can understand what it is you're looking at. If you look on the bottom, you'll see that each one of the model views had its own separate worksheet in Excel. So we can simply just go through and look at this. Now, this is a 2D view, of course, of the inspection report, but it gives the suppliers, a way to really understand what it is they're supposed to be inspecting. So this is the output a lot of our OEM customers are providing to their suppliers. Now, we also give you a 3D HTML report. This is very exciting, because what we're going to do, we'll take your inspection plan, your 3D model, your model views, and all the things that you're going to inspect. We out them to 3D HTML. All you need to view this 3D HTML is a web browser. No special software. You just generate that 3D HTML in our software, and anyone can view this. So it's useful for sharing information among companies, or sending it downstream. I'm going to fast forward just a bit here. Okay. Right about here. So as you can click on the annotations and they highlight in the bill of characteristics and vice versa. So you have, the links to the data. Now, the use case for this is for if you're going to start adding measurement results. So what am I entering in my Excel form? What am I doing here? So if we look at the balloon number 10, okay, we see it highlighted. We go back to the bill of characteristics. Oh, okay. This is the area, this is the characteristic we're measuring. So now we can just put measurement results into here and provide that data. Again, we're going to take this data back, but this is a nice, easy way for suppliers to work with MBD and actually see what it is they're inspecting and actually put the measurement results into their Excel form. So the green numbers mean we're within 50% of the tolerance. The yellow, of course, means that we're on the other side of that tolerance. And then red, of course, means we're out of tolerance. So, but yeah, these two work very nice together. You can see I've added a bunch more results here. Now we're going to close the loop. And this is the exciting part. Now we're going to come back upstream with this data. I'm going to simply import the inspection results into MBDVidia. And you can see we have this information in the bill of characteristics. I mean, the bill of characteristics really is the key of driving this data downstream and upstream. So we have some non-measurable things that have a pass-fail answer. We have the visual inspection information that pass-fails as well. And here we just go through, we start looking at the as-built data. It's overlaid and it's on the MBD. The QAF format supports the whole concept of QAF measurement results. So there's a nice place to do that, nice storage location in QAF for that. So now we're just going to go through and look at some of the different results for some of these characteristics. And really, this is what folks call the digital twin, right? Because you have your as-built data on your original MBD definition. You can start looking at some statistics here. You can do some individual charts, look at different results for those, maybe CPK or moving range, and so on. So, but that's the concept here is to go from, take this data, from your CAD system, balloon it, create your bill of characteristics, and then send it downstream. Okay. Next, I'm going to talk about the welding here. So welding, actually, you can also take advantage of MBD and welding. It can be used for downstream automation. Our friends at Visual Components will be showing you that shortly. We can generate weld reports directly from the MBD. Again, we go to the bill of characteristics with the weld information, and we generate, a plan. We can generate a weld export to some Excel form, and it becomes really easy to do with MBD. One of the nice things that also I just want to show kind of an end result here. What you're looking at here is weld results. So we have our weld data coming from NX in this case. We've got our bill of character with all the weld information in it, and we have some results here. And one of the things we can do with this is if we're in tolerance, if we're meeting the weld specification, we're green. Here, the length is not sufficient. It's not within the tolerance. So we actually can pop up a weld defect and show you that this is the proper weld length and the proper, based on the tolerance. So this is one simple example of bringing the weld data back upstream and marrying it to your MBD. Now I want to talk about non-dimensional quality. Here's where Kitov comes in. You can also you can do model-based definition with this kind of information. So again, it starts in the CAD system. You author this, you send it downstream. We do our bill of characteristics. We balloon that, and we send it downstream to Kitov, and then they send us data back. So you can actually include visual inspection information into your workflow. I'll leave that to Kitov, but I don't want to show you is again, the result that you can get out of something like Kitov. So here we have the visual information, visual MBD for these surfaces. Now, they were tagged in the CAD system and said, we need to inspect these visually. And what Kitov does is we send this data to Kitov and they send us back defects that they find. So you can see in this particular surface, they found 3 defects. You just click on the MBD, on the visual, characteristic, and they'll actually, we can actually show you where, like, here's a scratch. There may be dents or other things, but so the golden part is what it should look like. And this is the issue that they found with the visual inspection. So again, it's the same kind of concept for MBD. Really, you follow this workflow pretty much through, and it's just a matter of, well, how are you going to inspect this MBD data, and we can pull that all back in, and you can take advantage of that information. Okay, if you got any more questions on that, I certainly please contact me or Capvidia, and that completes what I wanted to share with you guys this morning. I'll turn it over to somebody else.
Thank you, Lyle. So to recap, what you just saw was MBD file, a native MBD file inside a Siemens NX, and you saw a plugin from Capvidia called MBD Connect for NX. It works within Siemens NX. You'll have a tab up at the top that allows you to click a button and export that native Siemens NX file to a QIF, right, to a neutral format. Once you have it in that neutral format, what Lyle showed you was the use of that QIF file in automated welding software, visual components, offline programming. Up next, we're going to hear from Brian. He's going to specifically talk about visual components and the capabilities of being able to consume that QIF file. But what Lyle showed you was once that automated welding process is done, you can then do an inspection on it. So through another piece of software, Kitov, that also takes that neutral format, that QIF file, imports it, and reads the surfaces that need to be visually inspected from that QIF file, which is defined in NX, exported to QIF, imported into Kitov, and Kitov actually uses that data to generate a robotic program to actually capture the views on the physical part that are needed, and then to recognize the defects that are there, and then to send that, encode that information back into the QIF file, which is what Lyle showed you in MBDVidia, in Capvidia solution, of how you can then see that inspection data all by using that QIF format. So up next, we have Brian Knudsen from Visual Components.
Good morning. My name is Brian Knudsen. I'm the sales manager for North and South America here.
We'll try and get rid of that echo.
At Visual Components. Visual Components is a company that's about 25 years old, located out of Helsinki, Finland, that has had a long relationship with another company you may have heard of called Delphi Robotics. Delphi and Visual Components have worked closely in the past, and Delphi was actually built off of the Visual Components platform. Recently, Delphi has been integrated and brought into the family of Visual Components and is now part of the Visual Components software. So Delphi will cease to exist in the offline programming world, and Visual Components offline programming will be taking over with it. With that being said, we also work in the simulation world. So here you can see a simulation that is running that is showing humans, conveyors, robots, turntables, pretty much anything you would need for a facility to be working. So while this is running, what we can do is we can actually generate all kinds of statistics. So right here, you're looking at production rates. We're looking at utilization rates for the different humans that might be in a scenario. We can even see what they're doing at any particular time. We can see this for robots, AGVs, conveyors, pretty much anything you can think of. And we can also do scenario analysis where you're going to be comparing, okay, what would happen if I had 2 people doing this, 3 people doing this, maybe an extra robot here, all different things that can be done. And the way we do this is by having an e-catalog, which has thousands of items in it. And right here, I have the FANUC e-catalog open right now for their robots. So all of these robots that you see here are FANUC robots, 148 of them, that are pre-made to FANUC's manufacturer specifications. So anything that they say they can do when it comes to joint speeds, accelerations, and joint limits, we're going to be building that into that robot. Along with that, we also have standard factory items like walls, components that you would commonly use, like conveyors, fencing, laser fencing, anything you can think of. Along with that, we also work, obviously, in the offline programming world. So an example of that is right here. So think about being able to program this cell so that it can do a particular set of welds without having to use the machine on a manual process of just using a pendant. Okay, so you're going to be able to sit inside of your office, program the entire weld routine, and then bring it outside or do a direct connection to the robots so that they can execute it. So to do a weld, just click on the robot, then we're going to zoom in on the weld that we'd like to do. So for right here, you can see a yellow line that's produced right at the joint. So we're going to click that just like that. It's going to bring it over. And on the right hand side, you can see all kinds of different parameters. So we can load a template that may have been previously made, that is how your company likes to work with particular conditions. So for example, thicknesses of certain steels, anything you can think of for the particulars of the recipe for making a great weld. So think of it like a recipe card. So within it, we can do things like the simulation parameters, we can look at the path, the lead in, lead out. We can also do adjustments with the wire angles, offsets, rolls, flares, things like that. Along with it, we can also control the different gantries, positioners, what you want to be the primary mover, secondary mover, things along those lines, and even things like how it's going to approach corners, go around them, etc. So right now, I'll hit play, and you can see it go in. It's properly avoided the edge walls. It's doing a nice weld, and it's going to rotate before it leaves, and then it pulls back out. Once we have this done, what we can then do is we can make translators or post-process it into translators that post-process it into certain languages. For example, FANUC right here, we can download a FANUC program, and it's going to create right here a FANUC LS file, just like you've probably seen before. Then you could port that over to your robot on the floor and have it made. So this already is a great leap forward in technology when it comes to generating these weld seams. But what we can also do is import a QIF file. So if you look right here to the left-hand side, you can see a QIF file that was previously made. And then we've got the software right here. And what we can do is when I start it, we can go up and we can import the template and the QIF file itself, and it's going to start building out all of the different weld definitions. So you can see them being generated. You can see everything is going to match just like they do on the left side of the screen. It's going to match on the right side of the screen. And then when we zoom in over here on the import example, you'll be able to see that the weld paths have all been imported, and you can double check to see what everything is already looking like. And it's going to be made into a format so that you can easily export it out to the robots, make any modifications, and do anything that you want so that you can have a better product. I'd like to thank you for your time, and if you have any questions, please feel free to reach out. My email is brian.knutson, KNUTSON at visualcomponents.com, and we will take care of you and answer any questions that you might have. Thank you.
Great. So that was a very, very quick presentation of some of the capabilities of visual components. Again, there was a software company called Delphi. They produced this offline programming solution that's built on top of visual components. And then Visual Components and Delphi have now, or Visual Components has purchased Delphi and is now offered this solution within their within Visual Components. Very, very powerful. Obviously, you saw some of the manual ways in which you can program a welding operation via offline robot programming functions within Visual Components. And then that gives you a very fine level of control as to how you want that process to execute. And then Brian went through the import of a QIF file that contains all the weld information. Having imported that QIF file, the Visual Components automatically generated all of the welding paths that robot has to go through. So all you have to do now is just a sanity check. Very powerful. I mean, you're saving tons of time here. You don't have to go through each one of the the weld seams, click your start and end point. All that's taken care of automatically. Again, using model-based definition. This is what we mean consuming MBD data. So up next, we have.
Good morning.
We have Corey Merchant from Kitov. And they're going to be presenting their solution for automated visual inspection. Corey?
Thanks, Nasir. Hope everybody can hear me. My name's Corey Merchant. I'm the VP Americas with Kitov.ia. And I'm going to go ahead and let Donna kind of run the slides so that we don't have any interruptions in the technology and presentation transfer. And we're going to talk about a lot of the same topics that you've been hearing with model-based definition, but we're going to approach it. What Kitov does is automated visual inspection. Okay, you can click to the next slide. So what Kitov is, we automate. Let me go ahead and turn off my video to save a little bandwidth. So we automate robotic guided vision inspection. Okay, and we can do that in a number of different ways, but what we'll be talking about today is from CAD-based definitions through optimal planning of an inspection plan to robust inspection itself, and then of course the digital record retention and transfer. And the way we do this and the main components we use, the technologies, computer vision, of course, we've been in this for 20 plus years, using optimal detectors that exploit part geometries. Where we specialize is really any 3D surface. We're not looking at the same PC boards at high speed down an assembly line. We're looking at critical components and assemblies that typically require quite a bit of human visual inspection. Advanced robotics. So our systems can ship with the robotics as part of the system, or we can work with any robotic platform that you may have. But our software is set up to make that very easy for the integration. You don't need robotic programming experience, for instance. Once we have that digital twin, that model in our software, then we know where the components are that you want to inspect, and we can optimize the robotic path and collision avoidance and all those things. It's an artificial intelligence-based system. We actually call it a hybrid. We use both classical machine vision and deep learning algorithms that we've created, and of course, model-based definition for the data transfer across the enterprise. Go ahead. So the way we see it, what are the challenges? It's really bridging between design intent and the actual quality. As we all know, product is designed, it should be perfect every time, right? Well, reality of it is, that's why we have to inspect, because sometimes it doesn't live up to its ideal. Then how do we generate 3D inspection plans fast and accurately? Historically, you can do what we're going to be talking about, but it takes days, weeks, even months. We can shortchange that process dramatically. And then how to accommodate variations in production and products, real world again, versus the defined world. When the product moves, when things change, how do we accommodate that without dramatic programming changes? Okay. Go ahead. So our solution, here you can see for the first time on the right, some of our systems doing inspection. Quick and intuitive 3D CAD-based inspection via model-based definition that we'll be talking about. Automate the inspection planning. That's where a lot of time is spent. If you're familiar with vision and inspection, especially if you're using robotic guided, it can take an extraordinary amount of time and very tedious. We worked very diligently to expedite that process and automate as much of it as possible. And of course, we say superior-based inspection, AI-based, and easy integration into both plant automation and enterprise data. So in other words, fitting into whatever the manufacturing floor requires, whether that's with a specific type of robotics, looking over an existing workspace, or providing a full turnkey cell solution. And then of course, as we've heard from Lyle and Brian, the data transfer via QIF files, which you can then share upstream, downstream throughout the enterprise. Go ahead. So Kitov technology really, in this respect, is in three areas. One is the automated inspection planning. So in this case, we will be displaying, how we can do simple and intuitive CAD-based marking. We call that CAD to scan. We're very similar to what you've seen with the Capvidia. We work very closely with them. Various CAD programs where you're able to mark what surface it is you want to inspect on a part or assembly right within the Kitov software, send that down to our system, and then perform the execution, supporting multiple CAD systems, and then of course QIF eventually for the data transfer. Then the inspection itself. That's really where we've spent a lot of our time over the years, is creating the very best images, which can then be used to make a decision. Is it a defect or is it a false positive? That's a fine delineation everyone is trying to achieve. As I mentioned, we use what we call a hybrid model, both AI and classical computer vision, so it's working right out of the box, but then it is going to improve over time as well. We can also do what we call on-the-fly camera-based accuracy corrections. Let's say that part is not positioned exactly the same each time. It's going to look slightly different. Well, we're able to recognize that through some validation scans and actually adjust the robotic movement so that we're still getting the best possible images without having to abort or modify the program. And then we'll talk about open software platform. And this is where Kitov really wants to focus on the software and work with partners or various technologies to import some of the best technology out there and combine that with our platform to really get the most powerful solutions in the industry. Next. So we'll go through this quickly. A lot of it is redundant. Model-based enterprise, adopting to what we call the closed loop. You heard that from Lyle as well. That's really kind of the end game, or what I call lights out automation. So we're able to embed that visual inspection data and the requirements into the 3D model, automatically generate the full inspection plan within Kitov, and then display the results back on that model again for going back upstream or downstream. And then there's that closing of the loop. You're getting feedback from the actual 3D manufacturing, manufacturing on the 3D models. That's where I call it that lights out automation. And of course, the data transfer through the QIF, I won't spend a lot of time since I think that was explained quite well. Next. And just visually how that loop is working. So we can send the QIF file to the Kitov system. And from that, we extract the inspection requirements that were created. In other words, the inspection plan, what it is we're going to inspect on that product. But we're also going to extract the 3D geometry. And from that, we utilize a lot of things that are beneficial or required for the inspection. Things like, path planning as a robot, collision avoidance. What is that environment? That dictates your tack time and things like that. And the end result, you're creating that inspection plan, sending it down to the system, and then you're going to execute the actual inspection. Next. So the way the workflow goes with anything, you're going to define what it is needs to be inspected. You're going to create that inspection plan, and then you're going to execute the inspection plan. And we'll show you here in the next slide, how Kitov does that. Go ahead and click again to start the video. So this is, as I mentioned, we call it CAD to scan. So this is actually from our software, same blade, aerospace blade that I think we saw from Lyle. And in this case, it's with SolidWorks, but you can literally go through in our software and select the surfaces that you want to inspect. Sometimes you want to run a brief inspection just in a certain portion of that assembly or part. I don't need the whole thing. So what we've done there, now we send this down to our system. This is actually from our system software itself, going through the scan. And now here you see that blade in question on a fixture and the Kitov system going through and taking the required images to complete that inspection plan that was sent down. So all of these things you're seeing here, position of the camera, the illumination elements used, the intensity, how many images are needed to create the actual images to make a decision. Is it an anomaly? Is it a defect? Is it a true defect? And then here's some of the images you saw in Lyle's presentation as well. We always present on the left the ideal or the golden part, and then on the right is what we've seen and what the system has detected as being different. And you can do a little bit of add a little bit of data here. Let's say that scratch is in a safe location underneath, the end user is never going to see it and it's not going to affect performance. You can actually say that's acceptable. Teaching the system moving forward. We give you some geo on the part where it came from, and then you can add some history of what was done as well. Next. And again, this is just a little more complex part. I believe it's a power booster on a EV, electric vehicle, and it shows a little bit some of the different things that we can actually detect in that as part of that visual inspection. In this case, the plan was already sent down much in the same way. Now we're going to be looking at a lot of the different, not just surface defects, but maybe missing components, bent pins, literally anything that a human really would be looking for as far as what that assembly is supposed to look like, as opposed to the reality of the manufacturing. In this case, a label printed correctly, damaged areas of the part. And of course, you could view this at the actual cell itself where the inspection has taken place, but in most cases, this is going to be viewed maybe in the quality office, could be upstairs, could be completely off-site around the world. Pull up all of the products inspected for that day, look through what the defects that were detected. And of course, there's an awful lot of data analytics that go with it, as you can imagine, that allow you to say, all right, why all of a sudden are we starting to get defects within this one area? Allows you to get to root cause maybe faster. Was it a process change? Was there a maintenance issue upstream in the assembly process? Vendor change, whatever that happens to be, you've got the data at your hands now to make some of those decisions. Why don't we go ahead and forward, Donna? So, as I mentioned before, Kitov likes to operate in what we call an open software platform. The software being the centerpiece, the secret sauce, if you will, that we've developed. And we do sell turnkey systems, as you saw. But here on the right, you'll see some other configurations that we work with, cobots, robots, whatever that happens to be to fit the actual assembly or manufacturing process. We can work with the different CAD programs, as we said, we're always adding those, same with the robots. The controls and communications, really we can integrate with whatever controls are necessary in that manufacturing environment. And tools and sensors, we'll show in the next slide that, yes, we've concentrated on the visual inspection, but there's no reason we can't integrate it with somebody else's technology. Kind of like, Brian was showing, and we talked about the welds. that could be a great area I could see to add to the Kitov system. Why don't we go visually inspect, but then also maybe get some additional data from the experts on welding verification. You know, we're not the experts in everything in the world, but we want to be able to tie into those things. Next. So over here on the right, you'll see some of that open software platform in action, if you will. In this case, there's a dual-headed camera system on the robot, one of which is our visual inspection and positioning camera. The other is a non-contact metrology lens for actual dimensioning and measurement. The way this is set up, you're creating your inspection plan the exact same way that we did with the blade. You're going to go through and select not only what areas you want to visually inspect, but also what areas you want to dimensionally verify. Checking a tolerance, you know, distance between two planes, distance between or ID, OD of circles, whatever that happens to be, that can be loaded into the inspection plan very quickly, sent down to our system, and perform both the visual inspection and the whatever it is that the other technology is assigned to do, in this case, dimensioning. Here's another example with a contact gauge, in this case, a bore gauge, where the Kitov is doing the visual inspection, but maybe more importantly, we're also doing what we call micro positioning of the head itself. So we take very fine images and make sure the head is in the right place before that contact gauge comes down, or the bore gauge, which obviously could damage the head or the product itself. So it's kind of dual purpose of what Kitov is doing there. Next. That's really kind of the quick run through of what it is we do and how we tie into some of this other technology. Last year, we were fortunate enough to win the Vision Award in Stuttgart, Germany, out of over 120 applicants and competitors for emerging technology for our CAD to scan to make visual inspection easy. We're very honored for that. And that's really the end of what I have. You can go to the next slide, I think is just, you can see my email address, just corey.merchant@Kitov.ia. If anybody has any questions, I'd love to follow up with everyone after the fact, but I really appreciate the opportunity. Thank you.
Thank you, Corey. So again, what you saw there was the use of the QIF file imported into Kitov software. And not only do they come up with the program path automatically to be able to get to the areas of the part that need to be imaged, but they're also able to obviously recognize through their advanced algorithms all the surface defects that are there. So we're talking about nicks, scratches, dents, you know, everything that perhaps that you're doing visually now, you can do in an automated fashion. So very, very powerful solution there. It's a couple of button clicks and you have a full visual inspection program and process. So up next, I'm going to be tag teaming with Andrew Blythe from PolyWorks. And what I want to show you today is automated dimensional inspection using structure light scanning. So what I'm going to do is I have a live demo set up here on the right. I'm going to change the right screen, the screen on my right here to the view so you can see the scanner software. And I'm just going to quickly run through scanning of this part. And then I'm going to hand it over to Andrew, who's going to walk you through the capabilities within PolyWorks to import, you know, native CAD or QIF files, more importantly, the MBD data, and then to generate extract the measurement results from that scan data. So Andrew, I'll just take a few minutes. I'll show the live demo and then I'll hand it over to you.
Perfect. Thank you very much.
I realize the folks in the on the back on my right may not be able to see the full demo here, but what I'll do is right after we're done, I'll set this up in a loop so the scanner's running. If you have any questions, you want to come up and see it, but you should be able to see the scanner screen up here. So what I'm going to do is I've essentially read in the MBD file, and we've translated that geometry into a robot program so that we can move the robot can move the sensor, which is attached to the end of the robot, through the various position it needs to go through to capture the features and to capture the data on the features that it needs in order to take the measurements. So what I'm going to do now is just literally execute the program. And what you'll see on the screen is as the scanner is projecting the fringe pattern on the surface of the part, it'll be calculating the 3D geometry of that of the surfaces that it sees, and you'll see those surfaces come in the 3D view. And as the robot is moving and the rotary table is spinning, you'll see more views being captured. Because it is a line of sight technology, it's only going to capture information on the areas that it sees. And you'll see a model being built up on the screen. I'm going to speed it up here a little bit. So again, what's happening is the scanner is actually flashing a fringe pattern on the surface of the part, and you can see that the 3D data is coming in. So slowly that part's being built up. We do obviously have the top surface that needs to be captured, and then what the scanner is going to do is the robot's going to position the scanner so that it can see the part from underneath, and then we're going to start obviously scanning the bottom side of this part. You're not going to be able to see the bottom areas come in just because of the way that the 3D graphics is positioned right now. But it'll be building up that bottom side. For non-contact inspection, it's a little bit of a different workflow, as you can imagine, than contact-based inspection. You don't have to physically touch the part, so you just have to have the areas of the part in the scanner view. So if I have a part, another bent sheet metal part that's of similar size, of similar geometry, I can literally use the same program and just put that part back on. So what the system calculated was the minimal path needed to scan all the areas. In this case, it maximized the use of the rotary table and minimized the position of the scanner head that the robot had to put it through. So the robot put it in one position, so you get the top down angle, and then the rotary spun, it did about 8 scans from the top, so 45-degree rotations. And then the second position by the robot was at the bottom, and then again, we took another 8 scans. So that's what it calculated to be the minimal number of views, so 16 views in total, to be able to fully reconstruct this part. Because it's non-contact, the size, there's no size limitation. You can go from 1/2 inch cube all the way up to, we've done cars, but you can go larger. The accuracies that the scanning system are able to hit are down to 1/10,000th of an inch. We can actually go smaller for real small fields of view if you're doing small parts or you have very small features that you need to measure. We can even get down into the micron range. So if you have any specific questions about the scanner, you want to see it, you're not able to see the live demo from the back there. Again, I will have this playing in a loop, so you can certainly come up and see it afterwards. But now that we've captured the 3D scan, I'm going to hand it over to Andrew from PolyWorks, who will show you how this data is used to extract all the measurements that are contained within the QIF file.
Excellent. Thank you very much, Nasir. My name is Andrew Blythe. I'm a corporate account manager with PolyWorks. And actually, to make sure we're on time and I'm going to hand off as well, like Nasir just did, but I'm going to bring in our CAD integration specialist, technical expert, Pascal, to show us a little bit about what you're seeing and kind of what Nasir showed with the scan there. Pascal, I'll ready to pass it over to you so you can share the screen and we can get right into it to keep the time where it needs to be. Thank you.
Perfect. Hello, everybody. I'm sharing my screen. Do you see it now? Or?
Yes, we see it.
Okay, perfect. So keeping in line with everything we saw in the previous presentation, NBD, digital thread, what we want to show is similar, but on the dimensional measurement metrology, basically. So we are in NX at the moment. We have an NBD file that has been defined in NX. So we have dimensioning added to it using the NX functionality, datums, GD&T, dimensions. What we have also is an extra plugin that we call PolyWorks PMI plus loop directly inside the CAD that allows to enhance your PMI. So CAD software are very good for most of the PMI, but there is some metrology features that are not easily done with the CAD. So we have added extra functionality, like for example, on this particular part, we have different views for the cutout with nodes, datums, planar face. I would like maybe to create another view for surface deviation. So typically, we know the designer told us at some location where he wants to have the part check for deviation. So that's those points here. So I can quickly add extra metrology control on those points to check the deviation on this part, for example. Using our list of characteristics, we can go modify the tolerance of those parts quickly. So instead of 1, we'll put 2, for example, just to go quick here with this. And what we saw also in the first presentation, it's possible to balloon or add characteristic number quickly in the CAD. So we have a one-to-one relationship between what the engineer sees inside his CAD software and what metrologists will see inside his metrology software. From this point on, you can save it directly inside the NX file. That's what I will do now, or in NX or any other CAD format. Or you could export it as a KIF file, as we saw for the blade in the first video. The outcome is the same. Once we have done that, we can now go to PolyWorks, that is our inspection software, when we can directly import this CAD file. So that's the one that is on the desktop, like 910, yeah. And you will see that in a few seconds, we got the part imported with the geometry, but also all the dimensioning requirements that were inside the CAD software are directly imported here. And all the objects that we need to measure to check those dimensions are already there. We got also the characteristic number, the balloon, so it's easy to do a match 1-for-1 if we have a defect, for example, on characteristic number 26. And what we saw also quickly appearing when we were doing the import is what we call an import log. And this is quite important because this is telling you what has been imported, what was not imported, and why. So as you might not have an X to go and double check what was inside the file when you did the import, that's one way to do a check, making sure everything has been imported correctly. In this case, we have 0 error. We have 10 warning. Most of the time, warning are notes that are human readable notes. So this note has been imported, that's been attached to the slot, but obviously this is something for a human to interpret and do something. This is not something that would be measured automatically. So that's why we say it has been imported as a custom control. So most of those warnings are those human notes. And as you move forward your NBD journey, the idea is to remove those human readable notes as much as possible to make everything as automatic, saving time and saving interpretation on what the note means. Now that we have this part imported inside Inspector, as you saw, I mean, we didn't see the live video, but I guess you saw the scan of the part. I already have a scan done for this part, so I would just import it on the desk from my desktop again. I've got my scan, and from this point, I just have to right-click and extract all the measurements. Same for my comparison point, where I wanted to check the deviation at certain location. And automatically, with the import, I also had my report created using the same view that we had inside the CAD. So basically, in a matter of minutes, you have an inspection ready to go on the shop floor and be inspected, or if the scan is available as it was now, that you get inspection results straight away with pass-fail results. So using NBD, you can really save a lot of time in the preparation of your measurement plan inside the inspection software. This used to be done by reading at the drawing and saying, okay, I need to inspect this circle with this tolerance. So it would be my balloon number 10. All of that had to be entered manually, adding new control, position, concentricity, diameter, etc., etc. So that was long. Now it's all automatic. I've got some warning here. I don't know why. Okay. So once this is done, following with the digital thread, this can be all uploaded to our database called Dataloop, where it can be accessible similar to what we saw earlier through a web browser. In this case, I will use Chrome. So basically, anybody in the company can have access it through the web browser. If we are coming back to engineering, directly inside the tool, we have a button that will connect directly to the data loop and look for this particular part so we can see the measurement results. So if I go there, this is starting a search on this particular part in the database. That's not the first time we do a demo with this part, so there is many projects already done in the database. So let's pick any of them. And now we are in a web browser and we have access to a 3D viewer, allowing us to show what are the defects using the same view that I had inside the CAD, inside my report. So everything is kind of tied together. And I can even have quick SPC calculation telling me, okay, I can see that my process was out of control. It's now more stable, but it's always close to the up, much higher than the upper limit, actually. So that's a quick way to, as we saw in the previous presentation, closing the loop, sending information directly to the engineer to see what the metrologist sees and take an action on that. So digital threads from the CAD to inspector, through our data loop database and back inside the engineering software to review the results. Not engineering software, but allowing from the engineering software to see the results. So that's basically what I wanted to show, how NBD, TMI, digital thread can allow you to save a lot of time at the inspection time and allow you to link back to the engineering. And just quickly, we use a scan here because that's what was used by in the presentation by Nasir, but those parts can be inspected also by probing, by CNC CMM, and we also have a lot of automation available to create the CNC CMM path. So everything is imported the same, but from there, we have what we call an assisted sequence that helps you to build the CNC CMM path instead of typically in the past programming it. Now it's a much more user-friendly interface to define all the CMM moves. So the first part is exactly the same with NBD. After, depending on which tool you want to use to inspect it, you get a slightly different result here. But after that, it's pushed to data loop the same way and visible inside the CAD the same way. So that's the closed loop of digital metrology using NBD, CMI plus loop, inspector, and data loop.
Excellent. Thank you so much, Pascal. And I'm sure like all of the partners that are working with CCAT, I probably could speak for all of them saying, man, time goes very quickly and there's a lot more we probably all would like to be able to share about the different solutions and how we play a part with the partnership with CCAT and the Digital Thread Lab. But that's a good high level for now for what we're doing here. And if you want more information or want to get into some of the nitty gritty of what happens when this happens, these different scenarios that I'm sure you guys are thinking about, feel free to reach out. I'm sure that Nasir and the great team at CCAT will provide information with this webinar as well. Thank you so much.
Thank you, Pascal, for that presentation, and Andrew. Again, what you saw there in PolyWorks solution are actually three different solutions. One is PolyWorks Inspector, which is the main inspection software from PolyWorks. And then you saw PMI Plus Loop, which is a add-in to pretty much any CAD. What you saw there was the Siemens plugin. So within Siemens, you have a tab, a PolyWorks tab that gives you the ability to export out or to actually generate the inspection program. And then you open that inspection program in Inspector. And now it's just a matter of, either automatically generating a CMM program, having now all the inspection information in Inspector, which is a workflow that we didn't show here. Again, to Andrew's point, if you have any interest in learning about that workflow, we can certainly arrange one-on-ones so that Andrew can demonstrate that capability as well. The workflow that we saw here was using 3D scan data, so a point cloud or mesh data imported into PolyWorks Inspector, and then extracting all the measurement values you saw instantaneously. If you have 2 or if you have 200 points, it happens all at the same time. So actually, the more measurements that you have to extract from that part, the more beneficial the more benefit you'll gain out of this non-contact workflow from PolyWorks. And then the third, solution that Andrew presented there was the data loop. So to be able to visualize the inspection data and have a link to it right from within the CAD, that's called the PolyWorks data loop. So again, 3 different solutions shown there. I know we're running a little bit short on time. We did want to give a couple of minutes for question and answer. So I'm gonna, if you have a question, please do raise your hand. I'll pass over the mic, and then let us know who you're directing the question to, and we'll have your question answered.
Hi, thanks again, Nasir. I just want to